Hello everyone, this is Group ENG6 Coders and my name is Jing. Our group chose the Steganography project, and the goal of this project is to build a steganography system that can hide at least 10 black and white images inside one RGB image. And we also created a GUI that allows users to embed and recover hidden images by using different embedded techniques. So firstly, let me just show you guys what did we do. And now you can see the GUI platform. And the step one is to just load the normal image. So you can hear the sound and we can load the dot image here. And then we can select 10 different images. For example, image one. Then we will see the hidden image here. And we have 6 different embedded methods. So let me do the odd even red first. So now the embedded image is here. And we can actually embed multiple different images. So let me embed 6 images here. Okay, so now I finished embedded them and we can do the recovering part. So firstly, let's recover image 6, image 5, image 4. And I can also show you what is image 3 so we can compare. Yeah, they're the same. So you can see the hidden image and recovered image, they're exactly the same. So our program works very well. And now let's talk about the GUI part here. So my job is just to connect all the functions together. So for the step one, we just need to get our original image, and we use the UniGet file here and read it and put it in the first image window. And then we want users to select which hidden image they want to use. So we build a drop-down menu here. And we have a hidden images properties, which if it is empty, we will just use the get hidden image function to get the 10 images file path. So the function is here. So basically, we will get the file path for these folders that contains 10 different images. And then we will get their full file path by using the for loop here. So once we get this 10 images information, when users select image 1, image 2, image 3, we can just put them in the second image window. So after this, we can move to the embedding and recovering part. And we actually have 6 different functions. They're odd even red, odd even green, odd even blue, and odd even mod 3 red, odd even mod 3 green, and odd even mod 3 blue. And these 6 functions are actually quite similar. So basically, we just need to firstly to flatten the hidden image. And then we store it in the properties in the embedded image, which is a cell array. So that makes it possible to keep track of multiple images. And then we just call the embedded function and we put the embedded image in the third image window. And after that, we just do the recovery part. And they're actually the same thing. So we just flat it first and then call the recovery function and put the final image in the last image window. So that completes the whole program, and I will just pass it over to Lydia and Sumaya to explain the code in more detail. Thank you.
Hello, my name is Lydia Mateza, and my role in this project was figuring out the bulk of the logic behind recovering and embedding hidden images using many different techniques that I implemented throughout. So in the RGB color scheme, there are 255 bits per color. What does this mean? This means that in each color, there's a spectrum from 1 to 255 that represents each color's virtual intensity. So for example, red would appear the most vibrant when all 255 bits are present, but will appear as black if no bits are present. The mixture of red, green, and blue hues are where magic happens. With 255 bits present of each color, the pixel will be the purest white. Conversely, with 0 bits present in each color, the pixel will show up as completely black. Mixtures within this realm of colors and bits will give magnitudes of all kinds of different colors. So many, that is, that to the degree where the human eye cannot process them in their entirety. The exact combination of possible colors can be extracted by multiplying 255 by 3, which gives us a value that represents the total number of colors that are available in the spectrum, 16.7 million. Quite a lot. Realistically, the human eye cannot perceive this entire available palette. Humans cannot differentiate 16.77 million different colors, not even close. This makes it possible to sneak in some data and create a virtual copy of an image if you're clever enough about it. The least significant bit is the rightmost bit that has the least effect on the value of the binary number. So the first embedding technique that I used was called the odd and even matrix method, also recommended through the project description, which basically hides data controlling the parity of the pixel values in a chosen RGB channel. The secret image is flattened into ones and zeros, and for each pixel, if the hidden bit is 1, the cover pixel is forced to be odd, and if the hidden bit is 0, the cover pixel is forced to be even. This ensures that the least significant bit directly reflects on the hidden data. And the second method is the mod 3 embedding approach, which instead encodes information based on whether the last digit of a pixel value is divisible by 3. Hidden bits equal to 1 are represented by values ending in 3, 6, or 9, while hidden bits equal to 0 are represented by values ended in digits not divisible by 3. Both methods work pixel by pixel. Adjust only small amounts to avoid noticeable changes within the image, and then write the modified channel back into the RGB image with a simple flag in the code deciding which embedding strategy is used.
So to go over the flattening and expanding part of our project, which is really essential to making sure that the embedded process is smooth, first we created a flatten image function that will take an image, an input image, and convert it to a grayscale, and then apply a threshold. So the pixels that are darker than the threshold will become 1, and the pixels that are lighter than the threshold will be 0. Which will help us end up with a cleaner binary mask. And this will also make the secret image much simpler and easier to embed, like I said. And then the expand image function will actually do the reverse. It will take that binary mask and convert it into a displayable RGB image. So the true values will map to black and the false values will map to white. So basically, the flattening will prepare our images for hiding and expanding will reconstruct them after recovery.